All right, so this is what the outline of our presentation looks like. And also, if you haven't been to a deep dive before, I'll remind you that our presentation isn't necessarily the deep dive part. We're just going to give you the necessary background to find your interest area within this big topic of alternative consensus and give you the prerequisite background information needed to really dive into our reading document. So I really urge you to take a look at that and see what interests you. All right. So yeah, I'm going to start with an introduction to consensus and distributed systems and a little bit into Nakamoto-Based consensus. And then we're also going to be talking about Byzantine fault-tolerant based algorithms, such as practical Byzantine fault tolerance, and also Tendermint, Casper, and federated consensus algorithms like that of Stellar or Ripple. All right. Okay, so we're going to start with what is a distributed system? And a distributed system is opposed to a centralized system in which the state of the system is stored on a single computer. But in a distributed system, the state is divided over multiple different computers, and because of that, it's more robust, it's more tolerant of failures, but it's often more complex, it's often more difficult to understand. So there are some common properties of distributed systems, and that includes concurrent components. There are different, say, nodes operating at the same time, and they often have to share messages back and forth in order to communicate the shared state. And there's also no global clock in a distributed system, and because of that, distributed systems are potentially asynchronous, which means that message delays and processing delays can be arbitrarily long. Another property is that there's potential failure of the individual components. All right, so the goal of a distributed system is to reach distributed consensus, and that means that all components need to agree on the system state. There's this concept of correctness of distributed systems, which I'll go into now. So in this seminal paper called Proving the Correctness of Multiprocess Programs by Lamport in 1977, he comes to this pretty basic seeming result about programs, which states that a program, or to prove that a program is correct, you need to prove two different types of properties about the program, safety properties and liveness properties. So a safety property is simply a guarantee that something will not happen. Yeah. So for example, if the program is started with the correct input, then it cannot stop if it does not produce the correct output. That's an example of a safety property. And you also need to prove that it has a liveness property, which is simply a guarantee that something must happen. And an example of that is a program will terminate if its input is correct. So if you're interested in why that's so, why you need to look for those properties, then go ahead and read the paper. Correctness of a distributed system is, what I consider correctness is achieving the program's intended goal. So the goal of distributed systems, as I stated earlier, is reaching distributed consensus. So correctness of a distributed systems is its ability to reach distributed consensus. And it can thus be described in terms of safety and liveness. In distributed systems, a safety property would be a guarantee that different honest components will never decide on different values, and we can refer to this as agreement. And a liveness property in distributed systems would be a guarantee that each honest component will eventually decide on a value, and we can refer to that as termination. As we stated earlier, distributed systems have potential failure modes. What I'll call fault tolerance is the ability of a system to operate in the event of a failure of one or some of its components. And a question is, can a distributed system retain its ability to reach consensus, correctness, and be fault tolerant at the same time? So in order to answer that question, we have to first figure out the potential failures of distributed systems. So I'm going to categorize them into network failures versus node failures. The most generalized network failure that we can talk about is just a loss of connectivity or a network partition. Let's take a look at this just generalized distributed system with, I guess, arbitrary amounts of connectivity. It's a connected graph. And let's say that this center node will just fail. And what we get is a network partition. We get this connected graph into this, it's separated into two subgraphs. And there can be multiple network partitions. If another node fails, we can get this disconnected graph, or graph of separate connected subcomponents. And between the partitions, the nodes cannot relay messages across those partitions. You can define a partition as at least two components of a system continue to run, but they can't communicate with each other. All right, and this idea of network partitioning relates to this pretty important theorem or impossibility result in distributed systems called the CAP theorem. CAP theorem, CAP, stands for consistency, availability, and partition tolerance. And consistency and availability are basically what we went over earlier as the safety and liveness properties of distributed systems, which are agreement and termination. So a consistency is a guarantee that reading from different nodes will return the same value. And availability is a guarantee that reading from any node will return some value. And partition tolerance is a guarantee that the system will still operate in the face of a network partition, which is what we just went over, across which some messages between nodes cannot be delivered. And that's this property of fault tolerance. The CAP theorem, which was introduced by Eric Brewer, who I think actually did research at UC Berkeley, he presented it at a talk in the year 2000, and he basically states that an asynchronous distributed system can at most provide two of the three guarantees at once. All right. Yeah, given a partition network, the shared state diverges and there will be a trade-off between consistency and availability. So as you can see here, there's a distributed system of 4 different components and there's no network partition. This system would be considered both consistent and available because it's consistent because they're all connected to each other in some way. So they should all have the same state and they should all be available as well. Because that's the default position. And then if we introduce a network partition, then one of two things could happen. Let's say we write in some value x to this side of the network, and we want to read from the other side of the network, and it returns maybe a previous value we sent in, or just some random value. So in this case, there's a network partition, and while both sides are available, they're not consistent. Or if you want to kind of solve for the network partition faults, what you could do is detect the network partition and then disable half of the nodes. And then in that case, we wouldn't be able to read a value from one side of the network. So in this case...
Lydia would like you to speak up a little bit.
Okay, sorry.
Or use a mic.
I'll just speak up.
Okay.
Yeah, in this case, the system is not available, right? Okay, so back to different types of failures in distributed systems. So we just talked about the general type of network failure, which is a network partition. And there also exist individual node failures that affect the system in some way. One type of node failure, mistype, whatever, is fail-stop nodes. Fail-stop nodes will just do as it says. They fail and they stop. So it could be a crash, a power outage, a hardware failure, or you ran out of memory or something. And these node failures play into this impossibility result called the FLP Impossibility, which comes from this paper written by Fisher, Lynch, and Partition in '85. their result was that both termination and agreement cannot be satisfied in an asynchronous distributed system if it is to be resilient to at least one fail-stop node. The proof is really complicated. It's super interesting. I recommend you read it in the paper. But as you can see, this seems pretty similar to the CAP theorem because we're stating that there's some trade-off between these three properties of fault tolerance, liveness, and safety. But the obvious difference is that in this case, the FLP impossibility proves this result for a system with only one fail-stop node, which is quite different than a network partition. Okay, back to types of failures in distributed systems. We were talking about node failures versus network failures. So one type of node failure was a fail-stop node. Another type of node failure is a Byzantine failure. And a Byzantine node can send conflicting information to different parts of the system. For example, it could flip a bit and memory, a node starts running a malicious version of software. So yeah, a Byzantine failure could be intentionally malicious, or it could just be accidentally conflicting. It's important to know what a Byzantine failure is in relation to Byzantine fault tolerance, which is a characteristic of distributed systems that can reach consensus in the face of Byzantine failures or Byzantine faults. And this class of failures was illustrated originally in the paper titled The Byzantine Generals Problem in '82 by Lamport, Shostak, and Pease. And it basically illustrates this scenario of a Byzantine army surrounding an enemy city, and they must decide upon a common plan to attack or retreat, and they all have to agree on the same plan, or else they'll fail. The problem is that there might be traitorous generals who send different votes to different generals. And an important question is what degree of Byzantine failure can be tolerated in a distributed system. Let's take a look starting from a base case of, say, n equals 1, n being the number of generals that we're looking at. So n equals 1 is trivial because you agree with yourself. N equals 2 is also trivial because if they both agree, that, or if there are no traitorous generals, then they agree. If there's one traitorous general, then they can't agree. Now, if we take a look at the case with n equals 3 and one traitorous general, say you're Lieutenant 1, and say Lieutenant 2 is the traitorous general, and say your commander tells you to attack on the left side over here, and Lieutenant is a traitor, so although the commander told him to attack, he tells you that the commander said retreat. So here you have two conflicting pieces of information, and then in this compared scenario where the commander is the traitorous general, he tells you to attack and tells the other lieutenant to retreat, and Lieutenant 2 is honest and tells you to retreat. You also have a conflicting set of information. And the idea here is that you can't tell, as Lieutenant 1, you can't tell these two situations apart. You wouldn't be able to tell who is telling the truth and who's lying to you. So in this case, this system is not Byzantine fault tolerant in the case of 3 generals with 1 traitorous general. The paper, the Byzantine Generals Problem paper, comes to the conclusion that no solution with fewer than 3 n+1 generals can cope with m traitors. And in other words, consensus is impossible to achieve if at least a third of the generals are traitors. This is a simple proof, but basically assume that a solution exists for greater than or equal to a third of the traitorous generals, and since it exists, you should be able to use that solution to solve the case of 1 traitor among 3 generals. And that would be a contradiction because we just showed that it doesn't work. The assumption basically is false. That's Byzantine fault tolerance. That's the Byzantine Generals Problem. And this is an overview of the impossibility results that I just went over with you. I guess I tried my best to kind of juxtapose the same properties with in between the cap theorem and FLP and Byzantine generals problem. From here, you can kind of see that FLP is more of a superset of the cap theorem because it proves a stronger impossibility because it assumes only one fail-stop node, whereas the cap theorem assumes a network partition. Okay. Are there any questions on this? I'm going to talk really briefly about Nakamoto consensus. If you recall, proof of work is Bitcoin's consensus algorithm, the original Nakamoto proof of work. And in this system, the concept of finding a block is also known as being the first announced valid block containing a solution to the mining puzzle, and that's linked to a previous chain. And the fork resolving policy is the longest chain. The longest chain is considered correct among multiple forks. Simultaneously found solutions and malicious mining does lead to forks, which are network partitions essentially, and the result is that different parts of the network contains different values. Nakamoto consensus-based proof of work favors availability or liveness over consistency or safety. Now we're going to take a look at Nakamoto consensus-based proof of stake, just a naive version, and this version of proof of stake is in this version of proof of stake, finding a block means that the consensus algorithm will pseudo-randomly select a stakeholder in proportion to its stake and assign it the right to create a single block pointing to the chain. And among multiple forks, the longest chain is again considered correct. As in the proof of work case, deviant actors will lead to forks that result in inconsistent network components, so again, favors liveness over safety. With this naive version of a chain-based proof of stake, I should say, we have something called the nothing at stake problem. And I'll go over this at a high level, and feel free to ask questions afterwards or whatever. In proof of work, we don't have this problem because we're using a resource external to the system to basically cast our votes. If we let H be the total hash power mining, then you have to split your hash power among forks if you are to mine on two different forks at once. Say 0.7 of the 0.7 of the total hashing power is being used on the upper fork, whereas 0.3% of the total hashing power in the system is being used on the lower fork. What happens here is the upper fork has a higher chance of finding a block. So let's say, the upper fork finds a block, and since it's now a longer chain, the whole network will move to that upper block, and now 100% of the hashing power will be used on that upper chain. With a naive version of a chain-based proof of stake algorithm, say we have S1 as the distribution of the stake in the upper fork, and S1 prime as the distribution of the total stake in the lower fork. And in proof of stake, you don't have this problem of needing to split your hashing power because in order to cast a vote, it depends entirely on your stake, which is internal to the system. Here you have nothing to lose if you mine on both forks at the same time. That's basically the nothing at stake problem. And this is illustrated perhaps better in these diagrams by Vitalik in a few of his articles. As you can see in the upper panel, say the left fork has a probability of 0.9 in finding a block, and the right fork 0.1. So obviously if you vote on either, your expected value is 0, and if you vote on just A, your expected value is 0.9. And if you vote on B, your expected value is 0.1. And you don't lose anything if you vote on both. So if you vote on both, your expected value is the sum of both, which is 1. Whereas in proof of stake, if you vote on neither, your expected value is 0 again. If you vote on A, it's 0.9, B, it's 0.1, but you have to split your vote because you're using your hashing power to vote. So that means you can only dedicate 0.5 of your hashing power to one fork and the other. So your expected value on voting in both is much lower than voting on A, which has a really high expected value. To solve this nothing at stake problem, we introduced this concept of slashing, basically penalizing people who vote on multiple forks. Early proof of stake chains, such as Purecoin, resorted to hybrid proof of work and proof of stake, or developer checkpoints. So far, we've only considered using like block rewards to reward miners. Now we introduce penalties and making a rule that you're only allowed to vote on one fork, and if you're caught voting on another fork, you get punished on this fork. Yeah, and that means you end up getting punished on both forks. Well, either you could say you get punished by voting on the wrong fork, or you could say that you get punished on voting on 2 different forks at once. It's up to the algorithm designer. Back to our previous example. Let's say we introduce this penalty, subtract 5, if you're caught voting on 2 forks. So now you're clearly disincentivized on voting on 2 different forks at once. So you could say this solves the nothing at stake problem. But it might take some time for a proof of malicious double signing to be detected. And during that time it takes for us to detect that, the double signer could have moved his money to somewhere else, could have exchanged it for US dollars. So there's no way to slash his money if all we have is this penalty. We basically have to introduce this concept of security deposits. So coins used for staking must be locked up in a security deposit, but we can't let it go immediately. There needs to be some holding time in order for us to detect this double signing. And this has kind of a negative externality where only excess capital can be used for staking, so it further disadvantages people who don't have that much stake in the blockchain. Yeah, and security deposits also can't be forever because people want their money back. We have this like intermediately long bonding period now, bonding and unbonding period. So let's imagine the unbonding period is 3 blocks. We have this new attack vector called long-range attacks. Yeah, say the unbonding period is 3 blocks. So we begin unbonding here, 3 blocks, and finish unbonding, the security deposit is released, and then the attacker just moves his money, and then forks back before his money was bonded. And this requires a lot of stake, but there are ways to get that stake, right? And the solution introduced by Vitalik in his initial proof of stake plan called Slasher is making the unbonding period a lot longer and also using this thing called weak subjectivity and exponential subjective scoring. But I don't really have the time to go over that right now, but it's readable, so I recommend you read this article. All right, so here are some Nakamoto-based proof-of-stake coins. Purecoin was one of the first ones. We have Next, Slasher, BitShares, Tezos, and Ouroboros. All right, so I think I'm gonna skip over these next few slides because we don't want to spend too long on this, but we have this new idea of Byzantine fault-tolerant based proof-of-stake, and that's based off of these Byzantine fault-tolerant algorithms that we had since the 80s and 90s, like practical Byzantine fault tolerance. Okay. Dave is going to go over those old algorithms like PBFT, and then later on in the presentation we're going to go over Tendermint and Casper, which also include either a hybrid or fully BFT consensus-based proof of stake protocol. All right, ready, Dave?
Yeah. Sorry. Okay, so to reiterate the problem for Byzantine fault tolerance, we have a bunch of nodes in a network. We want in this situation, we're gonna have a client. A client wants to have a request to the network. He wants all the nodes to be able to process the request and get the same outcome. But you also can't trust every node. Nodes could be malicious and send different data internally in their consensus algorithm to different parts of the network. So the main algorithm, well, it's not main. The one I'm going to talk about is called Practical Byzantine Fault Tolerance. This was made in '98. It's really the first solution to the Byzantine fault tolerance problem. That's practical. So what I mean by that is that it's computationally efficient. Previous solutions were extremely inefficient. So this it's about 3% slower than the unreplicated case, meaning for Byzantine fault tolerance, as Alex was talking about earlier, if you're going to handle F faulty nodes, you need a minimum 3F plus 1 nodes total. That, I believe, it's the FLP theorem. And then for PBF, I'm going to abbreviate this to PBFT because the name's really long. It provides safety and liveness given that a third of the nodes aren't faulty, and it requires, it has to be synchronous. As Alex was talking about earlier, we have a theorem that says if it's asynchronous, this is basically impossible to achieve. So first I'm going to try to talk about how as a client you're going to interact with the algorithm. First, you're gonna only talk to one node in the beginning, just because if you're going to try to message the whole network, that causes a lot of network lag on your part. So let's assume we have a perfect Byzantine fault tolerant algorithm. So you talk to the primary node. Oh, the primary node isn't anything special. It's just the point in the network who you talk to. You could pick a different guy to be your primary node every time. It's just the name we're assigning to the person you initially talked to. So let's assume we have a perfect algorithm here, and you've talked to the primary node. The whole network achieves consensus. How are you going to get your the result of this whatever you're requesting back? So if we had it such that every server was talking to the primary node, and then the primary node told you the outcome, then there isn't really any whole point. There isn't a point to this whole Byzantine fault tolerant algorithm, because this primary node could just lie to you to begin with. So this doesn't work. So how about if we have every server talk to you to begin with? Talk to you at the very end. So once they all achieve consensus, you get every server to tell you what they've come up with. So again, there's another issue here. You can still have the primary node who you initially talked to be evil. So a primary node can spoof everything about this whole situation. They can spoof the IP of the other servers. So we need something else on top of this. We need every server who's going to talk to you. We need their messages to be digitally signed. Does everyone here know what digital signatures are? If not, I can review them. Okay. So basically, we can confirm that the client can then confirm that the server is the one who is in fact telling who's giving the outcome back. It's not the primary node being malicious, because the primary node doesn't know the other people's private keys. So then this also, if you think about this for a bit, you might be confused why can't we have the previous situation in where every server is telling a primary node what's going on, and the primary node talks to you, but then the primary node's giving you their signed messages. The issue with that is that's trusting the primary node's going to work again, where we don't want any central point of failure because we want it to be Byzantine fault tolerant. So that's why we have to have every server talk to you at the very end. So let's try to come up with a naive scheme for how this could work. We know that at the end, every node has to tell you their result. So why don't we just have you talk to the primary node, you tell the primary node your request. The primary node tells every other node in the network what your request was. Everyone computes that result, and then sorry? So, do I have a question?
No.
Oh, okay. So, we can come up with a naive scheme where you talk to the primary node, you give it your request. It's going to relay your request to everybody in the network, and then every node computes the request and the result, and then tells it back to you. But there's an issue with this. The issue is you can't trust that the primary node is going to tell every other node in the network to write your message correctly. Because we have Byzantine fault tolerance, it can tell different people different things. And so let's say it did tell different people different things, then they'd come up with different states, and if they don't have any sort of consensus here, then they've essentially become faulty nodes for later in the future. They have to have the same state, otherwise they're, by the problem, they're faulty nodes. So this can't work. So what we can do to fix this is we can have you talk to the primary node, then the primary node goes and tells every node what your request was, but then we have a second layer where all those nodes tell each other what the requests were. So it's another layer of intercommunication. So is everyone following what I'm saying? I'm throwing a lot of models here, I know. So then we have, this sounds actually pretty reasonable, but then we have an issue here. We're dealing with a distributed system, so there's going to be concurrency issues. So if we don't enforce order, or after enough requests are going through, and there's network lag and such, you're going to have a concurrency order where a node is computing the request out of order, which then alters the state, and therefore the system's no longer safe. So we have to fix this. So how can we fix this? Well, one way is we could have another stage where the nodes are all confirming the order. So we could have the primary node give a specified order of when this should be computed, and then when all the nodes are talking to each other, that second step, they relay what the order is that they're going to use. And then every node is going to act on the order that they all picked. The majority order, like whatever order it receives from a majority of the nodes. So this again, like we're getting close to a solution here, but we haven't solved. This isn't Byzantine fault tolerant for nodes altering the order that they're specifying, because you can have different nodes telling other nodes different orders, and then. So then you can effectively convince nodes falsely what order to compute in. So instead, we need to have a way of enforcing order. So what we're going to have is another stage. So basically, this next stage, it's going to call the commit stage. So once all the nodes talk to each other, that's called preparing. And the node, every node is going to wait until they receive a lot of prepares that have the same order specified. Then, once they have a sufficient number of those prepares, they're going to send a commit out to every other node again that says, okay, I've received a sufficient number of people saying the same order that I received. And the key to this is that if you have faulty nodes or malicious hacked nodes trying to tell other people different things, if there's too many of them, it will never get past the prepare stage, because they won't send a commit to everyone else. So then, as a honest node, once you've received enough commits from everybody else, you're going to go and process the computation and tell the client. So there's a diagram to make this a bit simpler. Here, so the client has a request, and then the second pre-prepare stage, that's the primary node telling every other node, the request and the order it needs to be in. Then the prepare stage is all the nodes intercommunicating, saying that this is what I received. And then the commit stage is the nodes essentially certifying that I received a sufficient number of prepares that are all a sufficient number of pairs that are all the same. So at that point, then they can trust what they've been given. So then they tell each other, so they commit to each other. Once a node receives enough commits, 2f plus 1 is the number of commits you need to receive, because that's basically accounts for f faulty nodes. Because f nodes can just never tell you anything. Once you receive 2f commits that are all the same, you know that, okay, we've all agreed on this. So now we can go and compute and tell the client the response. So this is one way that you can achieve Byzantine fault tolerant consensus, and it's pretty fast. It ends up being only 3% slower than the unreplicated case, and that 3% comes from network lag, basically. And then there's another system that's commonly used, though it's not Byzantine fault tolerant. It's called Paxos. We have a ton of different types of Paxos. And in general, there's one type of Paxos that is fault tolerant. It's called Byzantine Paxos. It ensures safety and liveness, and it only handles, the main type of Paxos only handles halts. The faults it handles are a faulty node just not going to do anything. And so it needs 2f+1 nodes in total. So the reason Byzantine fault tolerance is important in distributed systems is because if a node's hacked, a hacker wants to disrupt the whole system, and so then they would tell different nodes different things. With Paxos, you don't support that most of the time, so you have to have a high degree of faith or trust that your software isn't going to be hackable in such a way that an attacker can get arbitrary code execution. And so, does anyone have any questions? I know I went through a lot. Yeah, yes.
So, in the Byzantine fault tolerance, you mentioned about the provided order. What does that exactly mean? It means the client, all the other nodes has to reply in a specific order? Or?
Oh, okay, sorry. No, the nodes actually don't have to tell the client anything in a specific order. What I meant by that is that, say we have 10 requests coming in, and they're all accessing similar transaction accounts. Then you want them to be processed in the right order. You don't want someone to be able to drain an account. Add money into a drained UTXO. And so you want to enforce that the order the server's processing it is the same. So the first transaction to take money out of an account is going to be the ones processed on all the nodes, not a second malicious transaction that's trying to pull money from that UTXO also. Does that make sense? Yes.
What about if you're just trying to reach consensus about a Boolean as opposed to transaction? Do you need that order step?
To be Byzantine fault tolerant, you do. That's the definition of this. If in general you just want a multi-party computation, then no, order isn't really important, and you could remove one of those rounds. Does anyone have any other questions? Okay, then I'm heading off to Jeremy.
Thank you. Alright, so I'm going to talk about Tendermint, which is it's another consensus mechanism that is sort of connected to a lot of this PBFT, Paxos, all of that. It's a lot more like that than proof of work or the randomized proof of stake. So Tendermint is a BFT consensus mechanism for arbitrary state machine replication, which basically means that it's not really its own blockchain or its own coin or anything like that. It's a library which can be used to build anything that you want to have where there's a state machine and there's transactions coming in that are changing the state, and you want it to be done in a Byzantine fault-tolerant way. And they do this in a way that gives you the liveness property when there's no partition, so as long as the network doesn't go down, and as long as 2/3 of the nodes are still running and connected to each other, transactions will be processed and everything keeps going as you expected. And I think the most important thing is that as long as no more than 1/3 of the nodes are Byzantine, there's always safety, right? Even if there's a partition, even if a bunch of nodes go down, it's not like Bitcoin where you end up with forks where people have transactions get included that later get removed because they were actually on a fork. And so yeah, it's safe and consistent in the event of a partition, which I don't know of any other blockchain system that has that property. I'm sure there are some, and this is the other thing, is that the way they built it, it is really easily scalable. It can run thousands of transactions per second, whereas Bitcoin is 5. And I think that's a pretty cool thing for it to have. And very low latency, at least in the experiments that they've been running so far with running stuff between data centers. We'll see how it actually works in practice. So we talked earlier about the CAP theorem. By the way, now that I'm getting into this, feel free to ask me questions at any point. Yeah, go ahead.
Are there any projects that are using Tendermint?
Yes. There's one called Cosmos, which is run by the people that make Tendermint.
And I'll get to it in the second half of this. It is very interesting and very big, I will say. Cosmic, yeah. That's sort of what they're going for. But yeah, feel free to ask any questions about any of the details of this. Yeah.
Are there transaction costs?
There will be, yeah. Yeah, I mean, it's not free, right? Like, if it was free, then everyone would, someone would spam it, and then it would fill up the thousands per second, and you wouldn't be able to get any out of it. So, like, there has to be some, cost always. Any other questions? Okay, so to the actual mechanism. So we talked earlier about the cap theorem, and it's always, like, talked about as, like, you can choose two of the three: partition tolerance, availability, or consistency. But it's not really that. It's like, you're on the internet, there are going to be network partitions, right? The network's going to go down. What do you do when there's a network partition? Do you go, okay, we don't have a quorum, we don't have enough of the validators online, we can't proceed, we just have to wait, and then maybe you end up waiting forever if some of those nodes got destroyed or something, or you just go, well, they might be gone, they might not come back, who knows, we'll just keep going, we'll process transactions. And if it turns out that we were on a a very small partition and we were creating transactions, the bigger partition continued without us and they made different transactions and we lose and our transactions don't get included at all. And that's what Bitcoin does, right? So if there's a network partition and America, Europe, and Asia all get disconnected from each other on the internet somehow, each of the the continents will keep mining Bitcoin on their own. They'll keep including transactions on their own, and then when all of the networks reconnect, one of those chains will be the longest chain. And everyone who made transactions in all the other chains, those transactions just didn't happen. And I think that's not a great thing. So yeah, network partitions can create forks that if you can't communicate, you can't decide which the longest chain is, and two chains can just keep going by themselves. And latency also does this. This is why there are orphan blocks on Bitcoin that, if you mine a block and someone else mines a block a tiny little bit later, you mine the block and you publish it, but it doesn't get to them before they mine a block. And so they don't know that a chain already exists, and so they make a fork, and maybe it's only one block of a fork, but it's still a fork. And if you put a transaction in their block and not in my block, well, then you lost out if my block ends up winning. And if you made the block time faster, like what Ethereum does, you would get a lot more of these orphan blocks, because the time that it would take for someone to find another solution gets a lot shorter, and it makes it more probable that while you're broadcasting your solution, someone else finds another solution, and you end up diverging. And larger blocks would have the same effect because it would increase the time it would take for a block to get through the network. So by choosing consistency, Tendermint actually makes it easier to have really fast block times and somewhat larger blocks, because they don't have to worry about, if I mine a huge block and it takes 2 seconds, by the time I get it to everyone on the network, someone else will have already found a block that is competing with mine. That doesn't happen on Tendermint. And so the way that works is with this. And so this is basically all of the actual technical material of what Tendermint is in one flowchart. And I like that they made this, so I didn't have to make it. But basically, the process of Tendermint is you start at the blue diamond new height. So there is some block that we've already agreed on. Someone gets to propose a new block. And who gets to propose it is done deterministically, so you don't have random people, different people proposing at the same time. For the new block, there's one guy, and he's the guy that gets to propose. He creates a block, he signs it, he broadcasts it out to everyone, and then all of the other validators, there's a time limit, but either they see his block within the time limit, and they go, yep, this is a valid block, it's validly constructed, it's signed by the right proposer, I'm going to sign off on this, and they do what's called pre-voting, and they sign that so that everyone else can see that it was actually from them. Or if they don't see a block, they pre-vote nil, which basically says, I didn't see a block in time, or the block I was sent was invalid, and so it doesn't count. And the basic idea there is that everybody gets to see the block, everybody sees, okay, it's a valid block, I'm going to sign off and there's a valid block, I'm going to move forward with this block. And then you wait for everyone else to send that message to you and to everyone else on the network. And then if you see messages from 2/3 of the validators, it's actually validators representing 2/3 of the bonded tokens, but we just say 2/3 of the validators for simplicity. But if you see messages from 2/3 of them saying, we're all pre-voting on the same block, then you know, okay, 2/3 of the network has seen this block, it's the same block that I've seen, 2/3 are in agreement that this is the block we're moving forward with, okay, good, I can move forward with it. And then you pre-commit to the block, which is basically the same as pre-voting, just doing it again. You sign another message saying, okay, I have seen 2/3 pre-votes for this block. I will now pre-commit to this block. And then you wait again, and you see that everybody, there's at least 2/3 pre-commits to the block. And once you've seen 2/3 pre-commits to the block, you go, okay, there's 2/3. We've committed to the block. And then it's up to the next proposer to propose the next block. And are there any questions on? Go ahead.
Yeah, so essentially do the checks in two phases, right?
Yeah, it's just it's basically just a two-phase commit.
Transactions in both
You really only validate them in the first one, because on the second one you're just checking that the hash is the same as like the block that we're all talking about. But yeah, it's basically just proposer. They make the block, they pick the transactions, they send it out, then everyone sees it, and if you see it in time, you go, yep, this is a valid block. I check all the transactions. I check that it's all consistent. I'm going to sign off on it once. You send that out, you broadcast it, you wait for a bunch of them to come back, and if you get enough of them, then you go, okay, a supermajority of the network is signing off on this block. I see that, I'm going to acknowledge that I see that, and then you wait for everyone else to acknowledge that they saw it too. And it's just this two-phase, like, this looks good to me, okay, I can see that it looks good to everyone, and then everyone can see that it looks good to everyone, or at least a supermajority. Yeah.
So yeah, I remember when there was the blockchain conference here at Berkeley, there was another algorithm called Algorand.
Yeah.
It did this in 7 stages.
Right, Algorand.
So how would you compare this to that?
Algorand is interesting and more complicated than this, and I really need to read that paper. I think the main difference between this and Algorand is doing random sampling. So they have a much wider pool of validators, and they randomly pick 1,000 of them to propose and create each block. And there's a part that I sort of left out here, which is the part where it says new round there. The basic idea is that if in any stage of this, either the timeout happens or you don't get a supermajority, everyone goes, okay, we didn't get a supermajority. Whoever's next to propose, they get to propose another block at the same height. And so you just go through that loop if you don't get a supermajority to agree on a block. And Algorand basically does that with their 7 steps. And the 7 steps is basically just saying that through some properties of the math, somehow, or I thought it was 9 actually. Might have been, I don't know. But basically they're just saying that we know that it'll terminate after 9 steps or 7 steps somehow. I don't really know how that works though. But yeah.
What's the protocol for choosing the proposer?
So the protocol for the proposer is, they call it a round-robin deterministic system. But basically, like, there's a set of validators, and each one has like some amount of bonded tokens. And the proposer is just selected sort of in round-robin style from all of the validators in such a way that it's proportional to how much of the bonded tokens you have. So if you have 1% of the bonded tokens, you get to be the proposer 1% of the time. And the way they do that is a surprisingly simple algorithm. They basically just have like, everyone starts at like a state of 0, and there's some like ceiling, and every round or every cycle, the amount of bonded tokens you have gets added to like your state value, and when your state value goes over the ceiling, you get to be the next proposer, and then it goes back to 0. And so like, it's a pretty simple mechanism, but basically all it does is mean that it goes through all of the validators, and each one ends up proposing proportionally how much of the total stake tokens they have. Yeah.
When you propose a block, do you put anything at stake so that if it's not a good block, then you get penalized?
Not direct. I mean, you do in the sense that this still has like the slashing stuff of like what Alex talked about with double signing and nothing at stake. So if you create a malicious block or you create a bad block, they will slash your tokens. But if you create a block that then doesn't go through, you don't, like, that's not your fault, that's the network's fault. So if you make a valid block, then you're fine. Okay, any other questions? Yeah.
Can you map the pre-vote and pre-commit steps to the prepare and commit steps from PBFT?
Mm-hmm. I'm not fluent enough in distributed systems to like prove it directly, but it seems very similar. Yeah. It's the same kind of thing of like a 2-step. We're going to vote on it, then we're going to vote on everyone's votes, and now we're all in agreement. Sure. So yeah, I think it's very similar. Any other questions? Yeah. So the validators, at the start of the network, it's the genesis block basically of like who gets what coins at the beginning, and that's the ICOs and all that. But then the idea is that to be a validator, you just have to bond tokens, and then you get to be a validator with that many bonded tokens. So it's up to you to choose. It's like you still have to get your bonding transaction included in a block, which means the existing validators could block you from doing it if they are all being malicious, but we sort of assume that no more than 1/3 are being malicious, and I think under any definition, blocking new validators from joining would be seen as malicious. Yeah.
the 2/3, is this like 2/3 of the network that's like running right now, or like?
No, it's 2/3 of all bonded tokens. So it's like, however many tokens are bonded in total, people who have ownership of 2/3 of them have to be in agreement. And the idea there is that if you made it just 2/3 of like whatever's online or whatever has interacted in the last n minutes or something like that, then you could create like problems of safety where you could push people off the network and then lower the pool size, and then you would have a majority. And so they basically just say, like, if someone has bonded tokens and they go offline, they are essentially a no vote for all blocks. And if, this is the thing, is like they got safety. What they gave up is liveness, that if more than 1/3 of the network, or if more than 1/3 of like the validators, if more than the validators representing 1/3 of the tokens go offline, I don't know how to phrase that. If a third goes offline, the network just stops, and you have to wait for them to come back. And
A third of the voters are unavailable.
Yeah. So like, if you've got someone with 10%, someone with 40, and whatever, if 33.3 whatever percent of the tokens go offline, then we just have to wait for them to come back, because that's enough like to block it happen. It's a veto, if you will. Any other questions about the mechanism? Yeah.
That means that if 1/3 gets attacked,
Mhm.
the whole network shuts down.
Yeah.
So how do you prevent that?
Well, it's up to the validators to make sure they don't get taken offline, basically. When we get to Cosmos, that's their sort of like party line on this, is like, yeah, you may be a target. If you get taken offline, that's your problem. And it's sort of the same with Bitcoin mining pools, right? Like if a Bitcoin mining pool goes offline because of an attack, either physical or DOS or whatever, DDoS, it's bad for the network and it's bad for them. And there's really no way for the network to protect them from the internet. And so they sort of have to figure it out on their own. It's the same with like, if your internet connection dies, it's like, well, that's on you. You need to have a better internet connection if you want to be participating. Which is why I'm not yet running a validator, because my internet is terrible. Yeah.
What proportion of the nodes are validators? And why would you ever not want to participate or have a...
That is the thing. I don't know if that's on the next slide or not, but yeah, so this is a cool graph, I think, because it shows some really high numbers for transaction throughput, which, range from, with 2 validators, you can get 14,000 transactions per second at max, but that's 2 validators, right? With 64 validators, you can get about 4,000. And that's sort of the key, right, is it doesn't scale to thousands and thousands and thousands of validators. It really only scales to about 100. And so, yeah, the proportion of validators relative to everyone else is going to be small. It's going to be 100, maybe 200 eventually. And when we get to Cosmos, their plan right now is to start with 100 and then increase it by 13% per year. So at the beginning, unless you are someone who has a bunch of the tokens and is willing to set up a server and have a good internet connection and have like, Cloudflare or whatever, like to protect you from DDoS, it's not worth it to like put in all the capital to do it unless you're going to be a consistent and reliable validator, because there's only 100 of them. And so that is, it's what you trade for getting 40,000 or 4,000 transactions per second, and getting the safety properties that we talked about earlier. So issues, actually, before I go on, does anyone else have any other questions?
Is there an unbonding period?
There is, yeah, and we'll get to that in like 3 seconds on this slide. Okay, so nothing at stake, right? Solve that with slashing anybody who double signs, which is sort of the standard thing to do. Weak subjectivity, long-range attack, that's the thing you just asked about, month-long bonding. So there's a bonding period of a month, so if you are a validator, you can't get your tokens out for a month, which means that anyone who is joining the network or been on the network, if they connect to the network at least once within a month, then they will be up to date on who all the bonded validators are, and they won't be at risk of an attack, what they call a long-range attack. It's still a problem that if you haven't connected in 6 months, then the validators from 6 months ago, there's nothing to say that they are still the validators, and they could have like unbonded their tokens, sold them, and then like sold their private keys to someone, and then that person could just change the history, and it's like, no cost to them because private keys with no tokens are not worth much. So that is a problem, and that's a problem with basically everything that has this weak subjectivity property. I think in the long run, though, eventually these systems are going to be so like integrated into how we use the internet that you're always going to be connected to it. It'd be like not connecting to like a cell phone network for a month, that like you might be out of range for a day or two or maybe a week, but you're not going to be disconnected from these networks for so long that it ends up being a problem. So anyway, any other questions so far? All right. So yeah, limited decentralization, talked about that a little bit earlier. At the start, it's going to be 100 validators, and then 13% growth per year in Cosmos, sort of on the assumption that we'll be able to build better network protocols to make the block transaction times faster, and we'll build, wider bandwidth tunnels and all of that. But it is right now a problem, and even with 13% a year, it's not going to be millions. But that's Bitcoin, right? Bitcoin is 10 mining pools. So 100 is better than 10, at least in my opinion. Now you can make an argument that Bitcoin doesn't stop anyone from mining by themselves, but no one does it because it's just not worth it. So I think 100 is better than 10, but we'll see. Any questions on Tendermint? Yeah.
How does one become a validator?
You own the tokens, and then you bond them, and then you run the software to process transactions.
So if there's a 100 validator limit,
Mm-hmm.
then you can just buy it. How does that work? Because you can.
So
How many
right,
tokens do you actually need to?
it depends on the network. Basically, if there are already 100 validators and you bond tokens and you want to be a validator, if you bond less than the 100th ranked guy, then you're not a validator. If you bond more, then he gets pushed out and you become the 100th validator. And I forgot to mention in all of this, which is unfortunate, there's delegated bonding, so you can delegate your tokens to a validator and let them work on your behalf. And presumably they'll charge a fee of some kind. But anyway, any other questions on Tendermint and the mechanism of it? Yeah.
I mean, if I could just buy my way into being bonded,
Mm-hmm.
doesn't that allow me to buy my way into potentially being nefarious?
Yeah. But you would have to buy 2/3 of the total staked tokens, which
Okay.
in theory would be a very large amount of money.
Okay.
My preference for this kind of thing is that you would make there be some limit on how many of the tokens need to be bonded. So you'd have to say 3/4 of all tokens have to be bonded, right, or something like that, so that you would have to buy a huge percentage of the market cap of the coin. Casper actually has a little bit of a problem with this in their ideas because they slash people even if for network errors, and there's a problem with that if you slash people for things that aren't their fault, they might just unbond their tokens and not bother, and then the total amount of bonded tokens goes down, and then the cost to attack is cheaper. And I think that's a big problem. But right now I think Tendermint is just based on percentage of total number of bonded tokens, which presumably will be a very large amount, because if you don't bond the tokens, then you're not getting basically interest or inflation on your tokens, and then you're sort of losing out a little bit. So, any other questions? Yep. Are we doing DPoS? I don't think we are. Not directly, anyway. It's not great. I don't know. Some people like it. I haven't read enough about it to really have an opinion, but I've heard bad things about it from people who like Tendermint better, so maybe that's biased. But anyway, any other questions? Yeah.
Transaction fee systems like
Mhm.
Tango, IOTA.
Yeah. What about it?
Because earlier you mentioned that you need these transaction fees in order for
Right, to not have people
obviously
spamming.
It's not technically a blockchain, so it's kind of different. But
Yeah.
I was wondering what's your opinion on that, or talk about.
I haven't read enough about DAG-based systems to really have much of a valid opinion on them. It's a nice idea. I need to read more about that. Anyway, so the next part of this is Cosmos, which is what Tendermint is being used for right now, or will be in the future. And so Cosmos is a network of Tendermint-based blockchains. And the whole, to me, the whole value of Tendermint is, one, it's got all the safety and it's got all the transaction throughput power, but then it's a library, not a coin itself. And using the library, the people who made Tendermint are also making Cosmos, and they're making, this thing that allows it to connect to existing blockchains by sort of putting Tendermint on top of Bitcoin or Ethereum or whatever. And then you can connect them all to a Cosmos hub, which also runs Tendermint, and then you can have a distributed exchange, which also runs Tendermint. And each piece of it can sort of tie into the same consensus mechanism that is really scalable and really, safe, right? It doesn't have the problems that you would have if you tried to build a blockchain network with blockchains that, if there's disconnections, then bad things happen. It's a lot harder to do that without the safety. And Cosmos also has sharding via zones, where they just have multiple Tendermint systems which are doing the same stuff, but are processing transactions separately. And you can even have them work with the same set of validators, so that you have the same security as like the main chain, as opposed to like, a smaller set of people who are validating it. So this is like a diagram of Cosmos from their promotional stuff. And the basic idea is that each of these would be a Tendermint-based blockchain. And the main one is the Cosmos Hub, and it sort of mediates all transactions through the other blockchains. So you would have like a Bitcoin blockchain, which is connected to Bitcoin, Ethereum, Monero, Doge, whatever. And then you would have the exchange one, which takes in tokens from all of these and allows people to do decentralized exchange. And they're still working on that part of it. I don't know enough details about how that part works, but I think it's a really cool idea that you could build something that actually directly connects all of the existing blockchains that right now are completely disconnected, and the only way to interact between them is through exchanges, basically. There's no mechanism. Yeah.
Have you looked at Polkadot at all? I don't know.
I've heard of it. I've been meaning to look into it. It's the same kind of thing. Yeah. Right. My understanding with Polkadot is it's more about atomic swaps, but I don't know, so don't quote me on that.
Chain of chains is where they
Right.
a multi-chain.
Am I going too slow? Oh, okay. Okay. Yeah. Do you have a question somewhere over there? I thought I saw a hand. Okay. So yeah, Cosmos is, I think, a pretty cool idea, and in particular, they have this thing called Ethermint, which is Ethereum on Tendermint, and so it's like the Ethereum virtual machine, right? Ethereum is just the virtual machine, and then also like their proof of work algorithm that they're going to replace with Cosmos. But if you take the Ethereum virtual machine and you run it on Tendermint, you have something that is basically like all the smart contracts, all of the all of the cool stuff you can do with Ethereum, you can do with Ethermint. And we'll see how that goes. And they are doing what they call a hard spoon, which is basically just like a hard fork, but it's less like contentious, I guess. So like they are working with Ethereum, and I guess them and Ethereum are cool about all this. And they are, when the Cosmos network launches, they are going to make a copy of the entire Ethereum like state, and they're going to copy it into Ethermint. And then if you have Ethereum, or you have any tokens on Ethereum, any ERC20 tokens, or any like multi-sig contracts or whatever, all of that is going to be on Ethermint too. And it will continue to operate exactly the same way as it does on Ethereum, just now on Ethermint. And it will also have like a contract that they use to create a token on Ethermint, which represents actual Ether, so that you can like there'll be a smart contract on Ethereum and a smart contract on Ethermint that allow you to like turn Ethereum into like Ethermint Ethereum and then move it to the decentralized exchange, and like a lot of really interesting stuff that would be really hard to do with something like Bitcoin because of the script system. But yeah, go ahead.
Is this similar to the concept of a relay chain?
Sort of, yeah. Well, I think the main difference is that because the Ethereum virtual machine has like such robust smart contracts, they're able to do a much more like deep connection between the chains. Like on this like slide, what I'm not showing here is that like each of these like side things, Ethereum is like the Ethermint one, but like the Bitcoin one, to do this sort of connection where you can send Bitcoin into Cosmos, you have to have something on Bitcoin that can receive the Bitcoin and then also send them back out. And that's a lot harder to do on Bitcoin. And so you have to do it with like scripts, and you have to do some really complicated stuff that I don't understand yet. But with Ethereum, you can do much more like powerful smart contract systems that allow you to like replicate the validator set on Ethereum, so that you can't like send out Ethereum from Cosmos without the validator signing off on it. And I don't know, they've put a lot of work into this that I haven't read, which I need to read, but I think it's a really cool use of this like abstract consensus layer that doesn't take any stance on any of like the blockchain stuff, like block size or emission of tokens or any of that stuff. It's just a consensus layer, and then from that you can build whatever you want. And so they're like, all right, well, we can use this to build things that connect to Bitcoin and Ethereum and Monero and like any other coin, really. And in particular, because Ethereum has a good smart contract and a good state machine, you can like really deeply connect it to Ethereum and sort of replicate Ethereum within it, and have all the smart contracts, but now with like thousands of transactions per second, and an even faster block time than Ethereum has.
So it's pretty much like Ethereum, but using the Tendermint consensus.
Right. That's exactly what it is. Yeah. It's Ethereum, but instead of proof of work or Casper, it's Tendermint. But then with the hard spoon, they're going to take the state of Ethereum when they launch, and they're going to copy it into it, so that if you have Ethereum or you have any tokens or whatever, you also have them on this thing, just to sort of like bootstrap the network.
Does this mean Vitalik's a big fan of Tendermint, or is he just treating it as an experiment?
I mean, I don't know him personally, so I can't say. But it seems like Cosmos and Ethereum get along pretty well. Like, they're not fighting each other. They're not putting out press releases, like taking shots at each other. It seems like they're working together on this stuff, sort of, which I like. I like less contentious stuff.
Well,
Bitcoin is kind of a mess, so.
He's working on consensus stuff.
Mm-hmm.
Variants and writing about it.
Right. I think, like, Ethereum, like, Vitalik and Vlad, they're doing Casper, and they're sort of doing their thing, and Tendermint's, like, doing its thing, and they're all sort of, like, they're in agreement about what the goal is. They disagree a little bit about the methods, but they're not, like, disagreeable about it. They're just trying to come at it from different directions, and I think that's nice, as opposed to Bitcoin, which is a lot of drama. And I was going to make some shot at Bitcoin earlier on, like, the graph of Tendermint, like, throughput, where it's, like, thousands, and I was going to put, like, a Bitcoin graph there, but you couldn't see it, because it's, like, 4 transactions per second now. And if you double the block size, it'll be like 8. So, like, an awful lot of drama for an extra 4 transactions per second. So I would prefer to go in something like this direction a little bit more. Oh yeah, any other questions? Yeah.
After the hard spoon,
Mm-hmm.
you need to synchronize the two chains.
That's the thing. When they do the hard spoon, they're gonna have like a copy of the state. They're not gonna keep like the state itself synchronized, but they are gonna have a smart contract on both of them that allows you to transfer Ethereum from one to the other. I don't know if they're going to try to also transfer like smart, like ERC20 tokens from one to the other. That would get really messy really fast, though, I think. But I know that they're not planning on keeping the two like synchronized, so that you can have like Augur or Gnosis tokens on one and on the other one, and then do what you want with them. And it's sort of like it's up to the creators of each ERC20 token to decide if they're going to do anything with the equivalent tokens on Ethermint. I think it'll be interesting to see what people do with that, because a lot of interesting possibilities there. Any other questions? All right, if not, I'm going to hand it off to Steven.
Thank you.
He's going to cover Casper. Thank you.
Cool. Okay. Let's go. So, yeah, let's get that out of the way. Cool. So, Casper protocol. Here we go. So, motivations for Casper. And Vitalik discusses how, really, for these systems to work, you need to have a defender's advantage. And the problem with, proof of work at this point is there is no defender's advantage. It's really a one-to-one kind of situation in which if simply the attacker can amass as much resources as the defender, they will overwhelm the system. And that's not a situation you really want to be in. Next one. So, proof of stake is a way of maintaining the defender's advantage. But if you look at the reasons why proof of work is running into issues with this, it's because of the kind of physical realities they have to deal with. Because they're just actually have physical constraints, it means that the constraints are inflexible. Whereas with proof of stake, you're able to design better systems such that really you can give the defender a better advantage, but also in the case of proof of stake, also make punishments much greater for malicious actors. So let me see onwards. Kind of a one sentence philosophy that Vitalik gives is rather than burning through security coming from burning energy, it really comes from the kind of economic value at loss that you have, the amount that you put up, the amount that you stake at for the chain that's accurate, or the chain that is going to be used. So rather than relying on rewards for security, it's relying on penalties. So any questions for these kind of hand wavy section? Okay, cool. Okay, so Casper really has 3 algorithms, and the first one is the one we're going to be dealing with primarily, which is the proof of stake algorithm. It also has an economic finality algorithm and a light client / sharding algorithm. And I'll focus a little bit on the implications of all 3, but really the focus of today's talk is proof of stake, because this is still consensus. So a property that proof of stake kind of offers is a fast block time, among other things. So while the current block time for Ethereum is approximately 17 seconds, with proof of stake, it's going to be 2 to 7.5 seconds. And what you notice about a lot of the parameters that are currently used for proof of stake is that there are a lot of ranges right now, and the reason why is they're going to be really testing and tuning these parameters. So when you ask me like, oh, what's going to be a specific parameter, I'm just going to be totally honest, it's going to be a range most of the time because they're just not sure. It has not been released, and the version that is going to be released is going to be very like they're taking a very conservative approach to switching to proof of stake. A second kind of feature of proof of stake when it's fully released is the kind of eventual removal of proof of work, and this has some real advantages just because of the energy and hardware overhead that you have to deal with. And just to kind of cite these fun examples of Bitcoin, like if it was a country being kind of 81st country in terms of energy consumption, like the kind of overhead that you're talking about here is massive. And Theorem is kind of similar. It's still like Moldova. So you're talking about very large overheads and talking about very large, very costly transactions that you really just don't need to have. So that's an advantage of proof of stake. For the economic finality algorithm, what you really have is a kind of policy that means that once a block is made over a certain amount of time, over a range, again, over an indeterminate amount of time right now, but validators converge on full commitment, which means that in histories that don't have that block, it's very costly for all of the validators. And this is very important so that you don't really have any history isn't changed, essentially. Then finally, the light client algorithm just ensures that partial nodes can also validate rather than just full nodes, which has many advantages. And also the sharding and inter-shard communication is another feature, which is just because Ethereum in the cap theorem really places availability over consistency, i.e. With many shards, they might not have consistent state, but it'll still be able to process transactions and still kind of continue working. Okay, any questions? Cool, onwards. Oh, yes.
Yeah, so I heard that at least for an initial release,
Mhm.
the POS will be on top of the
Yes.
proof of work.
Yep, it's every 100th block, there's going to be a proof of stake validator. So it's very gradual. They're going a very conservative route.
How would that work?
So I believe that it's going to be the same as proof of stake, but rather than it occurring in every block, it's going to just occur on the same process is going to occur just on the 100th block. So nothing's changing. Nothing's changing at all. And it's good that these two mechanisms are not mutually exclusive. That does seem to be features because all the incentives of proof of stake are kind of designed around proof of work to a certain extent. It means that they're compatible when it's compatible in this transition process. And I'll get more into that, especially when we talk about slashing and talking about the kind of penalties that are offered, because they're meant to kind of copy the kind of penalties you have implicitly because of proof of work, i.e. you have implicit costs associated with hardware and energy, and when you don't get a block reward, then you feel those costs. But proof of stake just makes those costs explicit because it doesn't have those kind of hardware and energy and electricity concerns. Yeah. Any other questions?
When are they rolling it out?
That's an excellent question. I believe it's going to be in. Do you have any, Ashwin?
I mean, someone
Yeah.
asked at the conference, and he said soon.
Yeah, that's okay. So that's what I was thinking.
Right.
Yeah, I mean, so I think the general response on all their blogs is that with engineering questions and just coding in general, it's often you deal with situations that's hard to predict the time horizon. So unfortunately, I think that's the best I can offer right now, which is unfortunate. It would be more fun if we actually had a deadline, but yes.
But is stake just essentially money?
Yes.
Yeah. So, but if we're talking about translating work to stake,
Mhm.
stake is fluid.
Mhm.
Are they talking about how to shield against people just giving other people money to take over the chain? Work isn't fluid. You have to do it yourself.
Mhm. I mean, yes, you could, but again, what we're going to be discussing soon is the kind of penalty systems that would really disincentivize any kind of move like that. Because with stake, what you're essentially doing is by offering, and we're going to get into this a little bit later, but I'll offer a summarized version right now, is by putting down for all the validators that actually can determine what's part of the chain, they have to offer a deposit. They have to put money out that kind of weighs in on what the history should be. And the more they weigh in, the more deposit they offer. If that block is not actually part of the final history, they lose a very large percentage of that deposit. So it means in the example that you just gave of let's say someone pays person X or malicious actor X a large chunk of money, say, change the history, let's do this. What would happen is if that block is not included, they would lose that a substantial part of that deposit. And especially even if you do succeed, another issue is like it's because of the property of, I believe, safety. Consistent with safety. It's possible to be able to trace or find the third validators who are malicious, such that if you do have a hard fork to change that history again, you can just delete their deposits. So like not only would the malicious actor in this case be like sought out, but also they'll lose a lot of money again. So it's by using this system of penalties, the intent is to really increase penalties and cost to any malicious actors. Did that answer your question, or?
There's a deeper philosophy question there about whether money really determines the reality of the chain.
I would add to that even with proof of work, you can use money to buy the hardware.
Just less liquid, I guess.
And then you can essentially do the same.
Yeah.
Right, but the reason to do that is to ensure independence.
Mm-hmm.
Right, so different groups doing work.
Yeah.
Let's talk after.
Sure. Yeah. No, I definitely discussed this after. So now getting into the more implementation or like the process of proof of stake. And you first have to initialize the Casper contract. And this is going to require a hard fork. And at the Genesis block, there is going to be a Casper contract that initially has a kind of hard-coded validator set and have a set of initialized parameters or set of variables. And only at this stage is it going to be hard-coded. Afterwards, the kind of validators and their actions and the kind of random variables they use will ensure that the validator set is at least pseudo-random. So it's very important for to ensure that the validators themselves are also available. Second kind of step is making the Ether deposit in order to participate as a validator. So all the validators that are included in the set have to offer a deposit. They have to offer a validation code that acts as a kind of public key, but later on in the process. The hash of this validation code is kind of used as a unique ID for them. And this is a unique ID that's used consistently through the process, but also on the blockchain as well. And then you have withdrawal address, which is after the deposit is sent back, after the kind of after you've in this either successfully gotten the block or unsuccessfully. This is where the money is returned to. So that's important. Let me see next one, and then confirming. The next step is like confirming the validator checks out. Of just basically if the signature that's offered in the start withdrawal function also is approved by the validation code, then it's cleared and you can continue. And fourth step is like kind of pseudo-randomly selecting the validator, and the contract does this. The Casper contract itself has the pseudo-random process for choosing the validator. And the odds are based on the fraction of total deposits they contribute to. So basically, if you offer a lot more like Ether, if you've staked a lot more Ether, you're also more likely to be chosen in the validation process. You also have, one other thing, which is if you, as a validator, don't respond to this process, after a certain duration, I believe it's 4 seconds right now, they then switch to a second validator. So there's like a limited amount of time in which you have to offer some kind of, in this case, a validation along with a stake, or it just basically moves to the next validator. Next is withdrawal, which is if you've done everything correct up until this point, that's when you are subject to your stake is now subject to two potential cases. One being that the validator produces a block and that is included in the chain, in which case you actually receive an award, like some kind of reward for picking the right chain. And this kind of increases proportionally with the stake that you've offered on whatever block that you included. And then the second case is if it's not included, in which case you actually receive the exact cost that you would have, rather than receiving an award, you receive the cost of that. So it's actually it's even both ways, even split if you're not included. What it means is you're incentivized in this process to begin everyone kind of jumping on to the weightiest blockchain, with the reason being that nobody wants to lose money. So unless you're explicitly malicious, for anyone else who just is a good guy, there's a real incentive to converge on one truth or converge on one chain. Any questions? Yes.
So when you say that the Casper contract will be added to the Genesis block,
yes,
that's not the Genesis block from the very beginning, right?
Or is it? I was under the impression, yes, it was. Yeah.
The question would be, do they have to redo all the hashes then?
I
don't think it would be the block.
Okay, maybe I wasn't aware that there would be a secondary Genesis block. I mean,
it would be Genesis block 4 proof of stake.
Yeah,
Like,
Okay.
Our first block.
oh yeah, it would probably do like
In the papers themselves, it said that it would not be included at runtime in a transaction. So perhaps it is hard-coded, like coded in some form of like, basically, I mean, that would make sense because otherwise, yeah, redoing all the hashes would be a tremendous amount of work, just infeasible. So, okay, that seems reasonable. Yeah, sorry. Okay, so any other questions? Okay, so there's a kind of, in this process, when you choose an incorrect block, it's called Dunkel mechanism, which is, in some sense, what you're, the reason why there needs to be a cost of choosing the wrong block is because otherwise you have like a nothing at stake situation in which a validator can choose every single possible chain and add a block to every single one of them in order to hedge their bets. Especially in this case because there's no hardware or electricity concerns. So in order to kind of simulate those in proof of work implicit costs of hardware and electricity, it's made explicit in this form, in which essentially if you've contributed to any blocks or any chains that just aren't included eventually, you will receive the cost for everything that's not included. So that is kind of, again, making these costs from proof of work that were implicit kind of explicit because they're artificial in this case. So yeah, any questions about that? It's kind of a...
By cost, you mean a penalty, right?
But yes, penalty. Yes. So kind of to a certain extent, yourself, because like the amount you stake is totally proportional to the penalty you receive. So yeah, so this means for any malicious actor, they're really, really intent upon trying to change this history or trying to go for a finality reversion attack. Again, like the risk and the cost increase as they're also as they're more dedicated. So
you can accidentally choose the wrong one, right?
Yes.
Network problems.
Yes, exactly. And this is exactly what Jeremy was discussing before, which is there are other kinds of frictions involved, which could be passed on to totally benevolent or totally innocuous nodes, and like that's probably something they're going to have to work on because otherwise, again, it's needless frictions. So, and in this situation, in proof of stake, fork choice is based on kind of the value at loss, which is the amount at stake on a particular chain. So it's not only about the length of the fork, but also it's about the weight at each block that determines what's finally accepted. So. And of course, the block rewards are, again, proportional to the total amount of ether actively validating it. So again, and what this means is because nodes and validators can verify what the weight is of these the different chains, again, it incentivizes people to choose one for there to be this converging history. And then, let me see. That's fine. Any questions? No questions? Okay, cool. This is where now slashing conditions come in, which is slashing conditions are kind of rules that are set down explicitly such that actors don't try something that could explicitly lead to misbehavior or like malicious actions. And basically, if you break one of these rules, you lose your deposit. Your deposit's burned. So that's where penalties also come in, is these slashing conditions. And there are kind of two guiding principles for slashing conditions, and one is accountable safety, and the other is plausible liveness. So accountable safety is when you can always track a third of validators and find which ones have violated slashing conditions. And this is very important because you need to actually, if you are threatening this penalty on deposits, you need to actually follow through. You need to actually be able to locate the malicious actor and to punch them. And so like if you didn't have this guarantee, then it's almost like at some point nodes would absolutely call your bluff. So, and then the second plausible liveness is when it's impossible to stop the protocol. There's no way of halting it such that you don't make progress. So together, if you have both of these conditions, you can not only align incentives by really preventing misbehavior, but also you can keep making progress. So an example of kind of like accountable safety, but without plausible liveness, is like imagine a situation in which you have a rule of 2/3 of the validators send a commit for the same hash, and then that hash is finalized. But you can only like send one. If you send 2 commits, you violate slash condition. So like for accountable safety, is it accountable and is it safe? It is, because if you have 2 hashes, they each have 2/3. It means the overlap is going to be 1/3. So it means that you can absolutely find the malicious actors, and it's just going to be the overlap between the 2 sets. But is it live? And the answer is no. If you separate, if like half of the validators accept like hash A and half accept hash B, what it means is that 1/6 of that of one side is going to have to slash itself in order to have approximately 2/3. And this is really bad because that isn't with any of their incentives to commit suicide. So it means that you can't halt this process. And then the opposite situation in which you have plausible liveness but no accountable safety is like, imagine a situation in which you commit to a specific hash at a specific time as well. And you have to have 2/3 of validators send a commit for the same hash at the same time. So in this situation, is it live? It is live. And the reason why is if you get into a 50-50 situation like last time, just do it again. That's fine. That's totally reasonable. But is it safe? And the answer is no. And the reason why is that you can have inconsistent finalized hashes in 2 different times. So that, again, you have a situation in which you have inconsistent history. So in the slashing cases, actually, I'm probably going to run through this pretty quickly because I feel like it's really non-trivial. In order to actually satisfy these 2 things, there are 4 explicit rules, which is a commit requirement, there's a prepare requirement, there's a prepare commit consistency, and then there's no double prepare. So like this, I admittedly really need to figure out the logic of this, and unfortunately, right before this presentation, I deleted the slide, but this is not updated, so that's a real shame. Does anyone have any questions? Questions? Yes.
Deposit amount constant, or how does it get?
Can you repeat that? Sorry.
Is the deposit amount just a constant?
Yes. Oh, I mean, it's constant once you've like committed it. Like once you've staked this amount, yes, it's constant. You can't change it. Is that your question?
Well,
or is it variable? Like you can choose different amounts to deposit.
because it says like essentially the slashing conditions will take away your deposit.
Yes.
Right? But then is that
With slashing, it burns through all of it, I believe, because it's slashing is like it's for the worst behaviors. It's for like behaviors that are seen as directly malicious. So like yes, your entire deposit is burned.
so why would you deposit more or less? Just to have more influence in the system?
Yes, if you're yes, that. I mean, also there is a reward as well. So like there is a subtle reward that means that you still make money if you commit more. So like if you have a lot of if you have a lot of ether and B you don't need it immediately, like i.e. you have enough liquidity that you just don't need it now, then why not make money, right?
So the reward is proportional to the deposit.
Yes. Yes, but the penalties are a lot, basically far outweigh the rewards. I believe that, I wish I included this graph, because basically the rewards are logarithmic, whereas the costs are linear. So it's a lot, the costs are much greater than the rewards.
So good actors have an incentive to stake more deposit, basically.
Exactly. So good actors have a kind of a tepid or warm, they have enough reason to not forego like liquidity and having a little bit more freedom of having ether now for basically interest per second. Like that's the term that's typically used, is like the interest per second of having this deposit. Yeah.
Kind of relates to what I was asking earlier about like group size and the penalties. So you sort of decide because you take a certain amount, but who decides on the scaling factors?
Oh, I mean these are all public. For the slashing conditions.
Yeah.
So these are all public. Like for instance, like there's only 4 of them, and like they are designed so that you like validators won't do this by accident, because it is a lot harsher than situations in which, it's very harsh because you're going to be losing.
It's decided by the people who build it.
Yes, exactly. Yeah. Yes.
So if everyone's being a good actor, where do the rewards come from?
I mean, I believe that the rewards will come from, there is a discussion of whether there's going to be issuance of ether as well as part of the reward. So like that's another kind of debate right now, is how that issuance process works, and whether it's, again, there's also a tuning question of just how much issuance you need in order to incentivize enough people to really make the system safe and consistent with itself. Yes.
Sort of along those lines, would they introduce like a cap on how much ether can be issued as any part of, or as a part of any new block?
Was it issued like as in?
Well, when you, I guess the rewards for successful validation, right, is like a percentage of new ether.
I see what you mean. Yeah.
Assigned to you.
Yeah. No, that's an excellent question, and I'm not sure. Honestly.
Yeah, then the inflation becomes variable. Right?
Exactly. Yeah. So like that's an excellent question. Like, and I bet that's I would love to know that as well. Because like, but I suspect that they will. I also like, because the scale of rewards is like logarithmic. It's like there are certain kinds of constraints. Albeit you're right. Like it's not I wouldn't be surprised if they impose more constraints, especially as they kind of gradually add proof of stake in and find if there are any issues when running it like real time. Okay, so another kind of issue is like weak subjectivity, which I think we've gone over already, have we?
A little bit.
Yeah, a little bit. Okay, cool. So just imagine a scenario in which the deposits are locked for 6 months. And if you have a successful attack within those 6 months, in some sense, the penalties still bite. And the reason why is that you can't go back and get to those deposits. So even if you're successful in the attack, once kind of the network is back, back up and running, or like basically your deposits can still be burned. But on the other hand, if the attack occurs after the 6 months, those deposits have been released. It means that the penalties in the system no longer bite. So one way of getting around this is by having kind of a revert limit, which is saying that nodes individually will prevent certain reversions that are beyond imagine like a revert X, like just a limit X. Again, this is something that's going to be tuned. And a kind of complication of this reversion choice, or like preventing this reversion, is that each node is making a relative choice based on when they first saw the block. So what it means is that all these nodes are going to be slightly different, but there's only really two cases in which this is really concerning. One is if the node is totally new and therefore is willing to revert because it's just never seen the block before. And the second case is if it was online for more than the reversion limit. So this is not like, it's important to realize that this is a problem, albeit the odds of it being exploited are very low. It's very difficult to have enough nodes that can really be exploited for real reversion. Any question? Okay, cool. When it comes to proof of stake attacks, there are two that were mainly mentioned in the papers. I mean, I guess it was a third, but it's a lot more subtle. So there's a finality reversion attack, which is when validators that have already finalized this one set of block, like let's say block A, then goes back and changes it to like A prime. And this breaks the finality guarantee. But kind of a response to this, a potential kind of partial solution, is if the community can kind of coordinate out of band, which of course is not ideal, but it's possible, and then choose which fork to kind of reinstate. And then the evidence of the attack will be there because of safeness. And what it means is that, again, a third of the validators that were malicious their deposits could be destroyed. And then for the second kind of attack, which is the liveness denial attack, it's if you have a cartel that's more than about a third, and they can effectively stop the finalization process. And two ways of getting around this. One is to have an automatic feature to rotate the validator set, which means that even if you have a cartel, like next period or next epoch, they can't do anything about it. And the second thing is, again, like the first case, to hard fork with new validators and then delete the attacker's deposits. So like both of these attacks have kind of like partial solutions. They're not ideal. Like you would certainly want to be working through the system to actually solve it, but both of these kind of rely on you coordinating out of band. It's not ideal, but still kind of can deal with them. Any questions? Okay, that's not. Just wrapping up now. So by moving away from these physical realities that proof of work has, what it means is that you can really change the rules to favor the defender more. In this case, by really having disproportionate penalties to rewards. Casper, again, kind of flips these incentives by rather than focusing on rewards like proof of work, instead really focuses on penalties and slashing. And then like kind of proof of stake deposits are also used as a mechanism not only for convergence for good actors, but again as a kind of threat to dishonest or malicious nodes. And then finally, these slashing conditions are ensure that not only dishonest validators are punished because they're known, like a third of dishonest or malicious nodes can be found, but also it can continue. Like this whole process won't be terminated; it will always be continuing, despite if you have kind of a lack of consensus in the short term. Any questions? Okay, cool. So here we go, federated consensus with Ashwin.
I have one for Cosmos actually.
Oh.
Do you have a token or?
Yes, they have a token called Atoms, and the ICO happened in summer, and they're not tradable, and they won't be until the network launches, which will be maybe in December, but maybe not.
There's another token, traded token for that.
Yeah. Wait, what?
Yeah, if you go on CoinMarket.
Oh yeah, no, that Atom is totally different. Yeah.
But
I
they
don't
have
know
the
that-
same name.
Right. Yeah, they kind of took the name, which kind of scammy in my opinion. But yeah, it should be live sometime soon.
Sure.
In proof of work, if someone obtains malicious majority,
Mhm.
then you're able to theoretically buy more hash powers and
Mhm.
overrule their majority.
Yeah.
What happens in proof of stake if a malicious majority obtains the majority of votes?
Sure. So I believe, I'm going back to, so if you have like a 30%, if you look at the largest exchanges then currently in Ethereum, if you have like a 30% participation rate, i.e. Malicious actors have 30%, you need like 4 of the major exchanges. If you have 40%, you need 8, and if you have 50%, it's like infeasible. So that's what I read at least. Yeah.
So everybody awake? No? I see a lot of computer streams hopefully following along. So we've talked about a lot of like technical implementations. Let's take a step back and go more general and go into like federated consensus. So here's just a comparison of the consensus we mentioned plus some others. One thing you really see is a lack of like flexible trust, right? Who do you want to trust? You don't want to trust the entire network, and maybe some asymptotic security and proof of work. Basically, one of them mentioned it. You need one-to-one. So basically, you don't want to trust everybody, and this becomes really important when you go into maybe where you don't, not necessarily public environments, but maybe more closed environments, such as like the 2 examples I'll go are Ripple and Stellar, and those are more one of them tries to be public, and then one of them tries to be a little bit more private. So what is actually federated consensus? Well, the difference between a Byzantine agreement consensus and a federated Byzantine agreement consensus is once again is that in federated Byzantine agreement, each node chooses who it trusts, and that's the main thing. Just forewarning, I'm going to be using majority of Stellar's terms. I don't know if any of you guys are going to be straightly like outraged by it. So a quorum is the consensus reached by the entire node, and a quorum slice is a subset of that you can reach consensus with. So in this case, you choose your quorum slice, and in this case, it shows right here that you trust 3 out of the 4 nodes. And then here are some other examples of different quorum slices that you can go. You can go to a tiered approach, or you can go into kind of like a cyclical graph. And then we go into some definitions, where we've been talking a lot about like safety and liveliness in this lecture. And I think it's important to say that in federated agreements, safety is kind of defined a little bit differently. A set of nodes enjoys safety if 2 of them can ever externalize different values for the same slot or the same parameters, and liveliness is if they can externalize new values without participation of any of the failed nodes. And let's talk about that more in the terms of a federated system. Safety. So safety is particularly important in a federated system because you need something we call overlapping sets. In this case, safety is not guaranteed because you have 2 disjoint quorum slices, and as a result, they can reach a different conclusion after the state update. So what you do need is you need something called like an they call it a interlocking set. And this would be, in this case, you have 2 separate quorum slices, but they both have in common V7, so that there's an assumption there that V7 would be able to coordinate within them, and then as a result, they would be able to reach the same safety. What about liveliness? Liveliness is something else in a federated system that you need to go into. Liveliness is only guaranteed for a node V if it has a quorum slice that is composed of all good nodes. So basically, all this sustains is that liveliness is once again the feature that you can come to a value, not necessarily whether that value is correct or not. And if you compose of all good nodes, then you can assumedly go to a value. And once again, liveliness, because of the federated way that the system is set up, liveliness is not a binary option for the network. A quorum slice can have failed without the entire network failing altogether. And then we kind of go to the voting mechanisms. We have 2 main implementations that do a federated Byzantine system. They both go rather than consensus reached through voting rather than any of the previous consensus protocols we've done. So there's a consensus protocol, and once again, you can show right here that where liveliness could fail is that if nodes broadcast a different ratified proposal. So what are some problems with like a federated consensus? It's no longer like a 1 CPU, 1 vote power, right? I mean, traditionally that's been the sense that each person has the same amount of power. In this case, once again, we go back to the other example of V7. The V7 has the proportion to disrupt the entire network just because he's the only intersecting node. So once again, certain nodes are valued more than others, and this becomes a problem because once again, if that node fails, then the entire network is disrupted. The other one is that security is pushed to the user's end. Once again we talked about is that quorum slices have to be well chosen. If they're not well chosen, you can run into problems where once again the network fails, or that you can reach an incorrect result, and it's all pushed to where the security to the user's end to choose good quorum slices. There's two current implementations of like a federated Byzantine agreement. One is Ripple and Stellar, and they work more or less the same. Ripple provides a validator set for you. There's about 100 validator sets, and as a result, there's some security implications that come into effect because most people aren't willing to change Ripple's actual validator set. On the other hand, Stellar, there's no validator set provided, and there's no minimum requirement. So and that becomes the problem that you're pushing it once again to the user's end to choose a good set for you. Questions? I guess that reaches the end of the lecture.